we're Team BioFood, and I'm Rigel.
I'm Yurkishan, and we're in grade 8
from Spectrum International School. Let's begin. I'm sure you throw food every day, but have you ever thought about all the negative effects it proposes? Currently, food waste creates 1/3 of human greenhouse gas emissions, and 1.3 billion people waste food annually. And I know you can relate to this. Food waste happens during the consumer and retail stages. It's the discarding of perfectly edible food. The further up the food chain people waste food, the bigger the negative impact gets, because all the resources and energy spent into making the food also get wasted. The average family of 4 spends $3,000 per year on food that does not even get eaten. But consumer behavior is the scariest part of it all. That's when most of the food that is preventable takes place through acts such as food spoilages, leftovers, or not planning and overbuying, and much more. Therefore, we decided to focus on this category. But that's not where our problem stops. We want to reduce food waste because we want to reduce the amount of landfills, because food waste in landfills accounts to 8% of the greenhouse gas emissions, and 24% of municipal waste is made from food waste. Municipal waste is waste from households. Therefore, we picked households as our stakeholder because there's more statistics. Out of 932 million tons of food wasted globally, 64% are wasted from households. And this is all over the world. In depth, in order for food to decompose in landfills, anaerobic decomposition takes place. This causes methane emissions, which is a gas 84 times more effective at absorbing the sun's heat than CO2. And according to the EPA, approximately 55 million metric tons of CO2 equivalent in 2020 was not captured by landfills. This just shows how rapidly and quickly food was wasted, as landfills weren't able to capture the gas because of how quick it was. If we focus on a more local level here in Kazakhstan, in 2024, 47.5 million tons of waste was collected by operating landfills in Kazakhstan. And if we look at a graph right here, we can see that in 2022, there were 3,229 disposal facilities in Kazakhstan. And among these, only 601 complied with the sanitary rules. But we decided to move on further and collect primary sources.
To gather some primary data, we conducted a survey with two household residencies with over 50 replies to gather some information about the reasons and the amounts of food waste to create optimal solutions to their needs. To gather some specialist opinions, we held an interview with the head of the school cafeteria, providing us with his opinions and observations. He mentioned that students often do not finish their food and that we should regulate the food portions and focus on preserving the leftovers for a longer time. Also, we held an interview with the school janitor, and the school janitor said that students, they leave a lot of consumable food around the school, and composting this food would be beneficial for us, making us energy instead of letting it decay in landfills. On this specific idea, we built on later. Our project aligns with multiple of the UN Sustainable Development Goals, which are the 2nd one, 3rd one, 7th one, 11th one, 12th one, 13th one, and 15th.
This is CoFood, our multifunctional fridge. And now I'll explain how. So we can see right after opening it, the shelves, which are for beverages, and then the trays for separations. But right underneath, we have ventilation to support coolness and airflow. However, the most important part is in the bottom, in the fruit section, with a drawer to pull and push back your fruits. The main compartment is the antimicrobial solution represented by the tea bag. For the antimicrobial, we will use citric acid as it's a natural organic acid found and widely used in food preservation. When it's applied as a coating on fruits, citric acid lowers the surface pH, creating an acidic environment that most molds and bacteria cannot tolerate. Antimicrobials also rupture microbial cell membranes and cell walls, which lead to cell death.
They interfere with spore germination, which is what makes microorganisms spread, and they also inhibit enzymes, which are used to break down food by microorganisms. Later on, we will add chitosan, as mentioned before, which is a natural polymer taken from chitin, which comes from the shells of shrimps, crabs, and other marine life. The chitosan will be used as it can form a thin edible film on the food's surface and will act as a physical barrier. And it also reduces oxygen moisture, which are two factors needed for microorganism growth. It also has a mild antimicrobial property, so it benefits us in all ways. The solution will be connected to a micro pump, which will be powered by electricity, so that the solution can be sucked out in a micro-measured dose accordingly. And it'll travel through a tube, and then through this tube it'll travel to a nozzle, and the nozzle will have a very small diameter, so this will create pressure, and therefore the liquid will turn into fine mist, which are extremely small droplets of liquid. Therefore, they are very similar to water vapor. And then the ventilation will allow the mist to gently settle on the fruits and vegetables surface. Moving on, we have these sensors on each floor. They'll use predictive modeling to guarantee the expiration dates of items that do not have dates according to when they're placed, but will also alert users on ones with expiration dates. Later on, I'll give an inventory for users to reduce overbuying, and we'll give suggestions to reduce leftover. That's all for co-food.
Modified atmosphere packaging is widely used in industries to elongate the life of a variety of foods, including meats, vegetables, fruits, fish, dairy produce, dried produce, ready meals, and so many other foods, while keeping the taste, texture, and nutritional value. Inside our main compartment, you can see the gas cylinders for nitrogen and carbon dioxide. To control the high pressures in gas cylinders, we use single-stage pressure regulators, which reduce and stabilize gas pressures to safe operating levels. After the pressure regulator, the tube connects it to the gas mixer, which precisely mixes two gases to create the desired modified atmosphere. After that, solenoid valves are placed, which ensure the timing of when the gases are inserted into the chamber. After the gases are injected, the heat sealer bonds the packaging material together and creates an airtight seal that prevents gas leakage and stops outside air from coming in. So users get a better grasp on how to use this countertop device that is adapted to households, we made a manual with safety tips and instructions. Before injecting the gas, the system has to remove air using an air pumper. This pumper makes it suitable for countertop devices because of its small volumes to match the capacity of the gas cylinders. For long-term usage, we created doors so users have access to replace the gas cartridges. On top, we have buttons for different food categories, which is connected to the gas mixer, which creates the necessary proportion for different food types. This process is being controlled by the program logic controller. Inside the chamber, we have two sensors. One which measures the pressure inside the chamber that confirms that air has been removed before gas injection begins. However, the second sensor verifies the correct gas mixture has been achieved.
To check the efficiency of modified atmosphere packaging and our ProGo system, we decided to conduct an experiment. We entered the lab with a hypothesis of modified atmosphere packaging, extending shelf life of food and reducing food spoilages. As research suggests that replacing oxygen with nitrogen and carbon dioxide alters the moisture, making the environment unsuitable for microbial growth and microorganisms, as well as reducing oxidation and inhibiting microorganisms. The experiment was reviewed and guided by our school chemistry teacher. And to ensure fair results, we used the same type of bread with the same mass.
As for the materials, we used 2 pieces of bread, baking soda, 100 milliliters of vinegar, vacuum flasks with tubes, 2 glass jars, 3 stoppers, 1 candle, 1 lighter, and gloves to avoid contamination. By mixing vinegar and baking soda, carbon dioxide was created. We wanted to test carbon dioxide's presence, so we connected the gas to a candle, which if it extinguishes, it indicates carbon dioxide's presence.
After injecting the gases into both of the jars, we decided on labeling them. Jar A had the carbon dioxide, while jar B had oxygen. Currently, our experiment is still ongoing and we are still observing our results. However, considering previous experiments and scientific explanations, our hypothesis should be proved right, as modified atmosphere packaging has features that prevents microorganism growth.
Thank you for your attention.
That's all from us.